Yeah. Hi everyone. Today we have Dakshita from UIC as our speaker. She's going to talk about cryptography with certified deletion. Let's welcome her.
So, I'm trying a new format for the talk. Please feel free to interrupt me if you feel like I'm going too fast or if anything doesn't make sense at any point. This is going to be about building crypto systems that have certified deletion guarantees. I'll explain what that means in a minute. This is joint work with James Bartosek, who's at UC Berkeley and who's fantastic. They're my own echoes. All right, so let me start out by just motivating the problem itself. The question is the following. Can we build an encryption scheme? For most of this talk, encryption will just mean public key encryption that has certified deletion guarantees. So in particular, there are 4 algorithms. The usual encrypt, decrypt, these are our usual public key encryption algorithms. But then additionally, we would like there to exist 2 more algorithms, one called delete, that intuitively allows a party that holds a ciphertext in their hands to perform some sort of destructive measurements on it in order to delete the underlying plaintext. So if you couldn't tell yet, this is going to be a quantum talk, and I will introduce quantum background. So again, feel free to ask me if you have any questions. Hopefully, I'll cover all the background you need to understand.
So what does deletion output? Is it B?
Yeah, this is going to be a certificate, which is a proof that deletion occurred. And then there is going to be a verification algorithm that obtains this certificate along with a verification key and outputs either accept or reject. And well, technically, the verification key is part of the ciphertext, so we can make it explicit. The encryption algorithm, in addition to generating the ciphertext, generates a verification key. In this work that I'm talking about today, the verification key needs to be kept private. So this is output by the encrypt algorithm, but the adversary can only access the ciphertext itself. And the verification key, you should think of it as private parameters that the encryptor needs to hold on to in order to later verify that deletion occurred.
So which terms are quantum and which terms are classical?
Good. So I'll usually use ket, this notation, to represent quantum states. So the ciphertext contains 2 parts. One is a quantum part and the other is a classical part. Decryption will take a quantum ciphertext in general that contains 2 parts as above and give us a message M. Deletion also happens on a quantum ciphertext to generate a certificate new, and verification is on the classical certificate and the classical verification. So it's only the ciphertext essentially in all of this that is quantum, partly quantum.
So, Dakshita, is there a reason why this certificate cannot be quantum? I guess maybe your scheme doesn't need it, but doesn't it make sense to define it could also be a quantum state as well?
Absolutely. So in fact, there are some works that were concurrent to ours that talk about quantum certificates. In general, it's easier to build schemes with quantum certificates, slightly easier. What we were trying to do, what we realized was that a classical certificate was also possible with our techniques. So we stuck to classical certificates. But that's a good question. And there's a work, I'll point to it later on in the talk, that considers quantum certificates. Okay, so informally, security with certified deletion means the following. It means that as long as an adversary A is polynomially bounded at the time of generating a certificate of deletion, then the verification of this certificate implies that the message underlying the ciphertext has been information theoretically removed from the adversary's view. Whereas prior to generating this certificate, the ciphertext for any public key encryption scheme, the ciphertext should necessarily contain information about the message that was being encrypted. And deletion implies that this information has been lost and cannot be recovered even by an unbounded adversary after this point. The assumption that we do still make a computational assumption. The assumption that we make is that at the time of generating the certificate, by performing whatever measurements that the adversary is instructed to perform, they were computationally bounded and could not break some underlying assumption.
For intuitively, what does it mean to the information theoretically removed? Like if I have learned B, a classical bit B, I will not forget it.
Great question. So indeed, like this captures forgetting. So let me move on to the actual experiment that will hopefully clarify what it means. So the experiment is indexed by a bit B. The challenger generates a public key secret key pair and encrypts this bit B using the public key of the encryption scheme and sends the ciphertext to the adversary. In the schemes that we will build, the ciphertext is going to be quantum. The adversary then, given this ciphertext, has information about the bit B in their hands. But the process of generating this deletion certificate implies that as long as the certificate accepts, this information has been removed from the adversary's view, or it's been forgotten, if you want to think of it that way. So the experiment that we look at considers an adversary that, given such a public key and a quantum ciphertext, outputs a deletion certificate, new, and a residual state rho. So rho is the state that they're left with after they have manipulated the ciphertext in this way to obtain the deletion certificate. And what we will say is that if the certificate verifies, then the adversary's residual state rho contains no information about the bit B. If it did not verify, then we can't say anything. That means maybe they didn't delete it, maybe they just kept the ciphertext around with them forever. So in that case, we cannot make any guarantees. So the specific statement that we have for certified deletion security is that the trace distance, which is a measure of how different these experiments are, in the presence of an unbounded distinguisher. So this trace distance is negligible in the security parameter K. Okay. So what do I mean? The experiment simply is you encrypt a bit B, send it to the adversary generates a deletion certificate. If it verifies, you output their leftover state. If it doesn't verify, you output bottom. And so now look at the state of the adversary when given an encryption of 0 versus the state when given an encryption of 1. These states are information theoretically close, statistically close, as long as the deletion certificate verified. So does anyone have any questions about the formulation or the definition? Elaine, did I answer your question?
Yes.
Is there I'm sorry, yeah, so is it the rows that are statistically close, or is it
Yes.
rows and the bottoms? We have like selectable boards, stuff like that.
No, we don't. So it is row, comma, bottom. So it's either row or bottom. So the output of the experiment is either row if the certificate verifies and bottom otherwise. And the outputs of the experiments are statistically close for B equals 0 versus 1.
So you have to decide between decrypting and producing the deletion certificate, right?
That's right. Once you've deleted, then the decryption is not very. Although there is a setting where it is, so I'll hopefully get a chance to get to it.
It's like the main application has some kind of timeless security, like let's say you want that completely, you already people will decrypt in 1,000 years, so you want to delete it in 1,000 years.
Yes, so indeed you can use this to build time-locked puzzles with certified deletion, which are moderately hard. So it's possible to decrypt it maybe in a year from now, but half a year from now you change your mind and ask them to delete it, and then they will never be able to. So that's one application, but I'll get to all of the applications on the next slide.
So there's
yes.
one question in the chat.
Yes.
We assume that the quantum ciphertext cannot be cloned in the first place because of no quantum cloning.
I'm not making any assumptions. This is just going to follow from properties of quantum information. So that clarified. Okay, so some of the applications of our main theorem, which I will tell you in a little bit, is going to be to compile schemes into schemes that also satisfy certified deletion guarantees. One example, and the running example throughout this talk, is going to be public key encryption. But besides public key encryption, this compiler also immediately helps compile commitments to commitments with certified everlasting hiding. That means you build a statistically binding, computationally hiding commitment, then ask the receiver to delete that information. And once they do delete it, if their certificate verifies, that implies that now the message that was committed is statistically removed from the view. It also helps with revocable time-locked encryption and attribute-based encryption schemes, also witness encryption, and finally, fully homomorphic encryption, which I want to spend a few seconds on. So an interesting use case of fully homomorphic encryption with certified deletion properties is the following. You have a server and a client. The client wants to delegate some computations to a server on some highly sensitive data. and wants the server to compute some function homomorphically on this data. So the client can very much do that. But then once this computation is done, the client can actually ask the server to information theoretically remove the data X from its view. And if the server complies and sends a certificate, then and as long as the certificate verifies, the client can rest assured that the server now has information theoretically lost all the data, despite having just computed on it before. Yes.
Can the encryption of f of x be possible?
In our scheme, it's not, because we also want to remove f of x from the server.
Right.
If it were classical, then the server can hold on to the encryption of f of x.
Right.
And that now any classical information they have, we cannot hope to, any information that is encoded within a classical ciphertext, we cannot hope to delete. Good question. Okay, and then one final application that I want to touch upon is everlasting security transfer. So all of us, or some of us, must be familiar with two-party and multi-party protocols, where sometimes it's possible to achieve statistical security against one adversary, but not both. So you do that at the cost of computational security against the other. And what certified deletion can do in the context of two-party protocols is enable protocols where to begin with, the protocol was secure against unbounded Alice and bounded Bob. This we already know how to do purely classically. But then Bob can transfer everlasting security to Alice, which makes it secure against unbounded Bob after that point and bounded Alice. So who can be unbounded switches after this transfer phase. And this is again a property that's unique to quantum protocols. Classically, once you computationally leak information about your message, you've leaked it forever. So again, any questions?
So by the way, is it clear that both parties cannot have everlasting security after the end of the protocol?
Yes, so there is an impossibility result by Unruh that shows that it's impossible to have everlasting security against both parties. So this is in some sense the best you can do.
I see. And is it easy to see, or?
No, it requires some work. It reduces to the impossibility of unconditionally secure quantum two-party computation.
Okay.
I can talk to you afterwards. Yeah, I don't think I can summarize it in a few words here. Okay, so I want to move on and talk a little bit about prior work. So I'm only listing the most relevant prior works. There's also some others that I'm not including here. Please look at the paper for more details. The ones that have looked at using quantum states to do deletion explicitly in the past is one by Broadbent and Islam, who built one-time pads with certified deletion. Actually, also there was a work of Unruh here, who built time lock puzzles with revocation, but using different techniques and with more complex assumptions than the one we use in our paper. Broadbent and Islam applied this to the setting of one-time pads, which is different from public key encryption. And the challenges are very different. In the setting of one-time pads, the message is information theoretically hidden from the adversary even before deletion. On the other hand, our challenge is that the message is present in the adversary's view, and we want to remove it. There's also this work of Hiroka et al. That builds public key and attribute-based encryption schemes with these types of certified deletion properties. They don't consider information theoretic removal though. They consider more key leakage style definitions, which says once the adversary has deleted it, you can leak the key to them and they would still not be able to recover the underlying plain text, which is weaker than our definition. And also they use different techniques. In particular, they need to make stronger assumptions and have much more complicated schemes than ours. So what I will hopefully show you is just a way to build a simpler scheme and prove security, prove a much stronger security notion. There's also this other work of Hiroka et al. That applies this to the setting of zero knowledge, which I'm not going to get into much in this talk, but our work also improves this work. And then there was some concurrent work, one of Khurana. There were two versions, one which was prior to our work, and then the other that was concurrent and independent update. And he builds proofs of deletion for learning with errors. Basically, the setting considered in that work is also the setting of fully homomorphic encryption. The key difference between our work and his work is he uses new assumptions on lattice-based cryptographic primitives, whereas we rely on standard learning with errors style assumptions. In fact, we rely just on semantic security of the encryptions.
Question?
Yes,
Can you say again, what is the potential application to ABE?
to ABE, right? So you can just build an attribute-based encryption scheme where the ciphertext of the ABE can be deleted.
Okay.
Does that make sense? Just standard ABE with this extra deletion property on it.
Okay.
And then finally, there is this other work of Hiroka et al. That was concurrent to our work that built certified everlasting functional encryption. So similar guarantees, but for functional encryption. And this was the work that had quantum certificates. And again, a much significantly more complicated construction. And all these complications in prior work were due to a conceptual bottleneck in proving a certain kind of removal of information. So before I get to that, let me give you some background. This is some quantum background. In this talk, we'll be concerned with two types of quantum states. The computational basis states, which are just ket 0 and ket 1, and Hadamard basis states, which are uniform superpositions over ket 0 and ket 1, which and are denoted by ket plus and ket minus. So ket plus is nothing but ket 0 plus ket 1 by root 2, and ket minus is nothing but ket 0 minus ket 1 by root 2. We'll often succinctly denote one of these four states by ket x sub theta, which is just ket x if theta equals 0, and ket 0 plus minus 1 to the x ket 1 if theta equals 1. So theta, in other words, denotes the basis. If theta equals 0, it is a computational basis state, which is just ket 0 or ket 1. If theta equals 1, it's a Hadamard basis state, which is ket 0 plus ket 1 over root 2. Sorry, there's a normalization. Or if theta equals 1, yeah, and x equals 1, then this is ket 0 minus ket 1 by root 2, which is the ket minus state. And now the facts about these states that we intuitively hope to leverage to build schemes with certified deletion are the following. First, if we were to take a computational basis state and measure it in the computational basis. So denoting the two types of computational basis states here, ket 0 and ket 1 by a horizontally polarized photon and a vertically polarized photon. And if you pass it through a filter that's also vertically polarized, then the horizontal one will not pass through at all, and you'll see a 0 on the other end, and the vertical one will pass through, cast light, and you will see a 1. On the other hand, if you were to pass one of these superpositions of 0 and 1, so the ket plus or the ket minus state, through a vertically polarized filter, then you'd see light with probability 1/2 and no light with probability 1/2. So essentially, if you take a computational basis state, which is ket 0 or ket 1, and pass it through a computational basis measurement or filter, then you obtain, then you learn exactly what the state was. On the other hand, if you take a Hadamard basis state, which is one of these two, and pass it through a computational basis measurement, then the outcome is 0 with probability 1/2 and 1 with probability 1/2. And this reveals no information about what the state used to be beforehand. So if you look at the post-measurement state of the system, it's exactly identical and independent of whether you started out with a ket plus or a ket minus to begin with. In other words, a measurement in the computational basis of a Hadamard basis state, of an unknown Hadamard basis state, deletes information about what state that Hadamard basis state was in, whether it was a plus or a minus. Similarly, a Hadamard basis measurement of computational basis states will delete information about what state they were in prior to measurement. And a Hadamard basis measurement of a Hadamard basis state will reveal full information about what the state was. So if this was a plus state, and you perform a Hadamard basis measurement, then you learn that it is a plus. And if it was a minus state and you performed a Hadamard basis measurement, then you learn that it is a minus. So the one sentence that I want you to remember from here is that measuring in the same basis, like from out of computational and Hadamard, measuring an X basis state in the same basis is going to reveal information about what the state was, perfectly reveal information in this idealized model that we're working in. and measuring it in the opposite or the conjugate basis is going to perfectly destroy information about what the state was. Now I want to motivate this problem of building schemes with deletion with a simple example of secret sharing schemes. And in particular, I want to look at something called a revocable secret sharing scheme. So this allows a dealer, Alice, to share her secret among two parties, Bob and Charlie. And as you can see, one share is quantum, the other share is classical, such that it satisfies the usual secret sharing requirements. So those are that any one share individually perfectly hides the secret. Both shares together can be used to reconstruct and obtain the secret perfectly. So that's usual secret sharing. But the reason we're doing this weird quantum stuff and not applying the simple secret sharing scheme is we also want an extra revocation property. So there can be a revoke mode where Alice simply asks one of these, the guy with the quantum share, to perform some sort of measurement, destructive measurement on their share, such that once this measurement is performed and the results of measurement are returned as a certificate of deletion, Alice is no longer, sorry, the secret is no longer present in the joint view of both players. Okay? So prior to this measurement, both could have jointly recovered the secret B. After this measurement, the secret disappears from their joint view and the joint view becomes independent of B, as long as, again, the certificate passes this verification check. So let's now try to build this revocable secret sharing object. As a first step, let's imagine just using these BB84 states that I just told you about. It's convenient that if you measure in the wrong basis, then you delete information. So let's just try simply having Alice sample one state out of the following four possibilities. So these are the four possible BB84 states. Alice samples one of them uniformly at random and sends it over to Bob. I'm denoting the one she sampled by ket x sub theta, where essentially she samples x randomly in 0, 1 and theta randomly in 0, 1. So by that notational convention, this just means if theta happens to be 0, then this is the computational basis state ket x. If theta happens to be 1, then this is the Hadamard basis state, which is ket 0 plus minus 1 to the x ket 1. Now, this has nothing to do with B so far. B is the secret she's trying to share. Also, given just ket x theta and not the measurement basis theta, this is not very meaningful. So let's send to Charlie the measurement basis theta, as well as Alice's bit B XORed with x. The reason we're doing this is Bob, if Bob does not collude with Charlie, which is an assumption we're going to make throughout, then Bob does not know theta. So this state that Bob gets, it can be shown that from the state, he has no chance of predicting what theta is. And so if Bob is asked to, let's say, measure this state in some basis, say the Hadamard basis, or either the computational or the Hadamard basis, for instance, then it is unlikely that Bob will be able to guess the right basis, first measure his state in the right basis theta, and use that to recover x and keep x with himself, so that later their joint view does contain B. So in other words, our goal is going to be to remove x from the joint view of Bob and Charlie, so that now given B XOR x, this is just uniformly random once x is lost. And to lose x, we will try to perform measurements. A problem with this very naive approach, which I haven't even outlined the full approach yet, but an immediate problem that we see is that Bob, given ket x theta, has a probability about half of guessing the right theta. So Bob just guesses theta prime with probability 1/2. Since theta is just a single bit, Bob's guess matches the theta Charlie had. So now what Bob does is measure ket x theta in basis theta prime. Now note that if theta happened to be equal to theta prime, by what we saw, the measurement will tell Bob x, and Bob can store this value x with himself for all of eternity. Later on, when they get together, Charlie, who has this classical information theta and b XOR x, they will be able to combine it and recover b, and that's not what we want. And so we want to prevent these types of immediate attacks where Bob simply guesses what theta is going to be. And the simple way to do it, which is what we will do in step 2, is repeat in parallel. So have many theta be a long string instead of a bit, so that Bob, even if he guesses a few positions, is not able to guess all of it. So what we will do now is sample x as an n-bit long string and theta as another n-bit long string. And then Alice sends to Bob get x theta. Now this simply denotes get xi sub theta I. So this is nothing but where xi is the ith bit of x and theta is the ith bit of x. Okay. And Charlie should get the basis theta as well as be XORed with all of the bits of x, for instance. So do here is say XOR the bit b with the parity of x. Because we believe that Bob is not going to be able to guess all of theta correctly and therefore guess all of x. And so if he loses a few bits, hopefully the parity is going to be a good enough extractor here and will help us hide the bit b. So now that we have a candidate scheme, let's try to understand how to revoke the secret.
So by the way, just to confirm here, Bob and Charlie can have arbitrary shared entanglement also, right?
That's right. Yes, Bob and Charlie can have arbitrarily shared entanglement. They're just not allowed to communicate after they get their shares. Yes.
And these photos, is it hand-drawn or you have taken it from somewhere?
No, it's hand drawn. Yeah.
Wow, nice.
Yeah, I can share them with you if you want to. Okay, so indeed, Bob and Charlie can be entangled. Thanks, Vipul, for bringing that up. All we require is that they do not communicate with each other once they receive their share. The reason we require that is if they are allowed to communicate, then Charlie can simply send theta to Bob. Now Bob can measure get x theta in basis theta, get all of x, write that down. This is completely classical information. And then no matter what you do to try to delete it like this, no way you can remove x. Okay, so now let's look at the revoke phase. Note that Bob had get x theta to begin with. He should process it somehow, and after processing should end up with this deletion certificate, which is a proof that he has gotten rid of x, and some post-measurement state row. And recall that Charlie already had theta and b XOR x. So we want that the joint distribution of the shaded states, rho and Charlie's state, which is theta b XOR x, and any other entanglement or prior state he shares with Charlie, this entire joint distribution should not contain b. In particular, that means it should not contain x, or should be statistically independent of x. And actually by x, I mean the parity of x. So sorry, let me write that up. So now, I know some of you were telling me you've seen the paper, but for those of you that have not, would you like to hazard a guess about how should Bob, what should this green box do? How should Bob prove that he has deleted the parity of x? One option is that Alice can send him some theta prime, which is different from theta, and ask Bob to tell her what happens if he measured in basis theta prime. Note that it's also important for Alice to actually check that Bob's certificate verifies. But Alice generated get x theta, so she knows what each of these states are in basis theta. Doesn't necessarily know what they are in basis theta prime. But anyway, this can still be made to work out. So theta prime will just be the Hadamard basis. So Alice will ask Bob, please delete, and in particular, the algorithm will be he should measure each of his n qubits that he has corresponding to get x sub theta in the Hadamard basis and report the measurement outcome to Alice. So his certificate mu is just the measurement outcomes. That is whether he saw a 0 or a 1 or plus or a minus after measuring get x theta in the Hadamard basis. And rho is any state that he's left with after he's finished performing these measurements. If Bob is being completely honest, then all he should be left with is just this mu, the same because it's classical. Of course, a malicious Bob could behave arbitrarily, may not necessarily measure in the Hadamard basis, and then could end up with some arbitrary state rho. But what we will try to prove here is that as long as mu verifies, Bob has information theoretically removed the parity of x from the joint distribution of what I just circled here. Okay, so now instead of proving security for secret sharing, I'm going to take another step further in terms of constructions and extend this intuition that we had for secret sharing, but to the setting of encryption. Now, the secret sharing construction has a really nice property in that one share is quantum and the other is entirely classical. That means if you had a classical encryption scheme, for example, you could hope to simply encrypt the classical share and release that classical encryption along with the quantum state. And because now you have one share in the clear, which is quantum, and the other share encrypted, this jointly should still hide the message M, which means this should still be a valid encryption. So building on that intuition, what we will essentially do to build encryption with certified deletion is to have Alice encrypt her bit B with two parts. The first is Bob's share, the quantum state get x theta, and then also release an encryption of Charlie's share. The reason we're not releasing Charlie's share in the clear is because then this hides nothing. So we do want to make sure that, for example, the bit B is hidden. Recall that Charlie's share was simply the basis information theta along with the mask applied to the bit B. This mask is B, which is the bit they want to hide, XORed with the parity of X. Now, for simplicity, for simplicity of proofs, also in the paper, we actually restrict to parity of X on indices where theta is the computational basis. So we only look at the parity of the computational basis states and ignore the parity of the other states. You can actually prove this also when you take the parity of everything, but we're going to restrict it this way. Please ask me if you have any questions.
Is there a reason why the measurements need to be done explicitly in the Hadamard rather than like a sequence of?
You could do it in arbitrary basis. It's just simplest this way. Yeah. So we just try to come up with the simplest possible scheme. And what we are doing essentially is saying to delete, you measure in the Hadamard basis, but actual information is encoded in the computational basis. So by measuring these computational basis states that you're being forced to measure in the Hadamard basis, we will actually ensure that you've deleted information. So brings me to the delete phase. Now, any adversary that holds this encryption, which is get x theta, which is Bob's share, and encryption of theta along with the masked bit B, can delete as before, as in the secret share. How? Just pass get x theta through a Hadamard basis measurement. You get the measurement outcomes x prime as well as a residual state rho. Now, the final thing that remains is how should we verify? So now Alice knows what x was and what theta was. So in particular, she knows which qubits were Hadamard basis states. So she will just check that the Hadamard basis states compile with Bob's measurement outcomes. That means for all I, such that theta I equals 1 or Hadamard basis, check that xi equals xi prime. And if this is true, then output accept, else output reject. So hopefully the verification and deletion.
I have a couple of questions. The first question is X random or is it?
Yeah.
Yeah.
X is sampled at random to begin with. Sorry, it's been a while since I wrote that, but yes, X and theta are both sampled at random to begin.
Okay. The second question is, if for some reason Bob knows the deletion certificate beforehand, does this violate secrecy? Can this violate secrecy?
So Bob is the one generating the deletion certificate, and it can only be generated after he has the ciphertext. So he cannot actually do it beforehand.
No, I'm just saying, just in case if he has a quantum state with him and somehow there is a leakage on the deletion certificate for some reason, like can he learn information about X?
I'll have to think about it. It will depend on what leakage you are thinking of.
I see. Okay. Okay. Mhm.
Yeah, I'm happy to chat afterwards.
Sure. Yeah. Thanks.
Thank you. Okay, so and I'm going to rush a little bit now. I don't have much time, but please slow me down if you have questions. It's okay if we don't get through a lot. Okay, so now let me just summarize what the encrypt, decrypt, delete, and verify algorithms do. To encrypt a bit B, you sample X at random, theta at random, create the quantum state get X theta, which is highlighted here, create an encryption of theta, and mask the bit B with X's corresponding to computational basis states. To decrypt, decryption is pretty easy. You can decrypt by first decrypting the ciphertext that encrypts theta to obtain theta, then computing X, because you're given get X theta, and now you know the basis theta. So to compute X, you simply measure each of these qubits in basis theta to find the string X. Now compute the parity of X restricted to theta equals 0 and XOR with the decryption of this second ciphertext. So decryption is basically just reverse all these operations that you did to encrypt. Nothing very deep there. Deletion is interesting because to delete, note that the ciphertext is this stuff shaded in yellow. So the only quantum part of it is get X theta. To delete, you simply measure this in the Hadamard basis and return the results of measurement. That's the honest delete algorithm. The hope is that an adversary that is trying to perform these measurements is going to have to guess which ones are the Hadamard basis states and which are the computational basis states. Now, this information is present in their view. In particular, the encryption of theta reveals exactly which are Hadamard, which are computational. But because it's hard to extract this information from the encryption efficiently by the security of encryption, our hope is to show that no matter what then the adversary does, they can't do much better than making a random guess about which is Hadamard, which is computational, and that guess will fail unless they're measuring nearly everything in the Hadamard basis. And if they do measure all these qubits in the Hadamard basis, then they've necessarily deleted information from the computational basis states by measuring them in the wrong basis, and that has destroyed, whether it was a 0 state or a 1 state in the first place. So that's going to be our intuition. Yes.
Is it important that you also encrypt the XOR parity?
It's an excellent question. It's not necessary. We couldn't prove it, so it's not clear. It reduces to some combinatorial conjecture which we tried to prove for a bit, but then couldn't. So we decided to encrypt it to make our life easier. But it's not clear. So that's a really great question. Yeah, you could leave B XOR with parity theta equals 0 X in between. And in particular, we couldn't prove semantic security. So what we struggled with was not proving deletion. We just couldn't prove that this is a secure encryption scheme anymore. The whole thing. So, okay, so the final verification algorithm, again, we've already talked about this. So we look at the certificate mu and check that it matches the verification key on all indices where theta I equals 1. And the verification key, you can think of it as the original X and theta information. And verification passes as long as Xi matches the certificate on all Hadamard basis positions. So is the intuition and the construction clear to everyone? So in the time I have, I want to say as much as possible about how to prove this. And this is something that we were stuck on for many months. So it looks simple, but it turns out to require some new insights. Recall what we want to prove is the following. Consider this experiment B, where the adversary obtains a ciphertext encrypting with B, then deletes it by sending a certificate, the certificate is checked. If it verifies, then we output the adversary's residual state. If it doesn't verify, then we output bot. And we want to say that the trace distance between these two experiments is negligible in gamma. Again, another way to interpret this is just to say that the probability that any unbounded distinguisher can distinguish between these two experiments is at most negligible in gamma. Let me write out what we want to prove. So I'm rewriting the same experiment, except I'm substituting the generic ciphertext, etc., with our specific scheme. So what happens is that the challenger computes a public secret key pair, computes a masked bit B, sends to the adversary the ciphertext. So you've all seen the ciphertext a couple of times now, but it's just this part, get x theta, along with an encryption of the basis theta and an encryption of the masked bit. Now the adversary performs an alleged Hadamard basis measurement, but the adversary is adversarial, so they could be doing something arbitrary to it to come up with a deletion certificate X prime and a residual state row. And if the certificate verifies, that means X prime matches X on Hadamard basis positions, then we output the adversary state, otherwise we output what? And formally what we want to show is that these two experiments are closed for this particular scheme. The one thing I want to note here is that B, like we had said in the beginning, so like some of you have said, B is in the adversary's view to begin with. Why? Suppose A was unbounded, then it could recover theta and B prime, use theta to measure and recover X, use X to unmask B prime. B prime is after all B XORed with the parity of X. So use that to unmask and recover B. So before generating the certificate, the bit B is information theoretically determined by the state that the adversary has. And yet we want to say that after deletion, it has been removed. So the first thing we do in order to make headway is that we defer the dependence of the experiment on the bit B until after the adversary generates their deletion certificate. So instead of defining the experiment, instead of using B in the early on in the experiment to generate the ciphertext, we'll generate the ciphertext independently of B. And then later on, once the adversary has deleted, we'll check if they got the right B. Let me explain what I mean. This experiment will sample B tilde, which is a random bit, uncorrelated with B, and now encrypt B tilde instead of encrypting B. Okay, so B prime is now going to be masked, a masked version of B tilde instead of being a masked version of B. And then later on, once the adversary has or has not produced a deletion certificate, so once the deletion phase is over, we will check if B tilde happens to be equal to B. So what is B? B is like a parameter of the experiment, which we have ignored up until after the adversary produces their deletion certificate. If these two match, then we'll do the same thing as before. If the certificate verifies, you output the state, otherwise output bottom. And if they don't match, so if B tilde was wrong, it was not the right B, then the experiment just outputs bottom. Okay? So we've just said that is a different way of thinking about it is we're going to guess what the bit B is, work with our guess until later on in the game, and then we will check our guess. And if our guess is correct, we continue. If not, we abort. Okay? And
who is guessing here?
The challenger. Sorry, by we and the challenger. The challenger guesses bit B. Even though they know B, they just want to defer the dependence of the experiment on the bit B. This is going to be helpful because we want to talk about removing B, and we can't even start talking about removing B until we make the experiment independent of B in the beginning. Does that answer your question? So who is B is the challenger.
So who generates the B2 or?
Yeah, the challenger samples the B tilde on there.
Oh, it's challenge.
Yes.
So by the way, is there a difference between this and just picking B prime at random and just defining B tilde later accordingly?
Yeah, no, it's the same thing. That's what I'm going to say next, but I just want to view it this way because I want to say that it's okay to sample B tilde first and then check your guess, because with probability, at least half your guess is correct. And so if So there's like a factor of 2 difference between the trace distance between those experiments where we depended on B to begin with, and these other experiments where we sample B tilde independent of B and then check. So in particular, the trace distance of these new sets of experiments is going to be half the trace distance of the original set of experiments. So that's the only reason I wanted to look at it this way. And then we can do what Vipul just said. Another way to think about this is that B prime can be random. So because B tilde is random and B prime is B tilde XOR the parity of X, this is just same as saying that B prime can be sampled randomly to begin with. And then once we learn, once we get the deletion, the so-called deletion certificate, we can check if B prime decrypts correctly to B or not, abort if it's incorrect, abort if the B prime we guessed was wrong. So any questions so far? Okay. So now in the next phase, we will purify the experiment. What that means is that we will, instead of performing measurements early on, we will defer some of these measurements to later. In other words, recall that the challenger was sending ket x theta here. On the next slide, we will replace this with halves of EPR pairs. The only differences from the previous experiment are written here in red. So in green, we have stuff that is same as before. In red, we have stuff that is different from before. So instead of sending these BB84 states, which are fixed to either ket 0, ket 1, ket plus, or ket minus, what the challenger will do is sample many halves of EPR pairs. Now, I haven't told you what EPR pairs are. These are entangled systems of qubits that are of the form ket 0, 0 plus ket 1, 1 by root 2. And the interesting thing about them is that if you measure one of these qubits in the computational basis, then the other qubit collapses to the exact same value in the computational basis. And also this is true for Hadamard basis. So if you measure the first qubit in the Hadamard basis, then the second qubit collapses to the exact same value in the Hadamard basis also. The reason we're doing this is so that the challenger basically gets to keep a copy with them of whatever they're sending over to the adversary. And now they can look at their own copy locally and reason about it. And this is going to be helpful.
Wait, so you're using the entangled property of quantum to prove this?
Yes, but it's not part of the experiment. This is just in the proof.
Okay.
So instead of the actual adversary, you're thinking of another adversary which is doing the CPR setup.
No, so the adversary here is the same. I'm just changing what the challenger does or how we view what the challenger does as first generating EPR pair halves and sending these to the adversary instead of sending ket x theta values. And these are the same distribution. So they are really, it's the same, the adversary is seeing the same view. Except we now have a copy that the challenger can use. So
does that make sense to think about B is half of the EPR pairs and then
yes,
they look like only just 0 and 1s. There's no plus and minus.
So no, so halves of EPR pairs are actually maximally mixed states. So that means you can think of it as a 0 or a 1 with probability half each, and equivalently as a plus or a minus with probability half each. Does that make sense?
Their density matrix is identity.
Yeah. Which is also the density matrix of an equal mixture of 0 and 1 and an equal mixture of plus and minus. So these really are the same distribution. In other words, if I sample uniformly from this set, here's the set. Oh, shouldn't have started scrolling. But yes, if we sample randomly from the set 0, 1 plus minus and send as a random sample, versus if we send a half of an EPR pair, it's the same distribution from the perspective of the receiver. Yes.
I'm very sorry, we might need to wrap up in the next like 3 minutes.
3 minutes? Okay.
Yeah, sorry about that. They're getting kicked out of the room normally afterwards, so.
I see.
Unless they're not coming. If they're not coming, then
Yeah. Let me try. Okay, so you have to believe me. Just a small leap that sending half of PPR pairs is the same thing. And it also lets the challenger keep a local copy that then they can stare at and draw conclusions from. This is a really helpful trick. It's not just used in our paper, it's also used in works on OT, and there's a whole literature behind this. But yeah, so we just send a half of an EPR pair instead of sending the state get X theta. Or everything else that is sent to the adversary is the same as before. So the stuff in green is unchanged from before. And now the next step in the proof is the challenger measures their halves of the EPR pairs, their own copy, in basis theta to get X. So what this experiment has managed to do is defer the decision on what X is to afterwards. So it's slowly trying to do things after the adversary has already generated their deletion certificate. And the reason this helps is that, actually you'll see, so let me rest. So yeah, so measuring AI in basis theta I to get Xi then allows the challenger to check if B tilde is correct or not. So check if B tilde is B or not. This is something we were already doing in the previous experiment. We've not decided on B, we were only deciding whether we got the right B later on. Here we've said, well, let's also not decide what X is. Let's just send a half of an EPR pair, which is maximally mixed. And then later on, let's measure it to see what X happens to be. And then use that to check whether we got the right B. Okay. So now it turns out that this experiment, again, is the same as the previous experiment. So all we need to do is prove that these two experiments with bit 0 and bit 1 are close in trace distance. And by now, there's no X. There's no X until after the adversary has finished their deletion step.
So does the challenger look at its own whole part of the error?
Yes, that's how they get X.
It is obvious because you're measuring things after the adversary has done something to B, so
Yes.
X has also kind of changed.
Yes, it is. Yes, but one can show that it is the same experiment by purity. So I can talk to you after.
I won't understand.
No, I'm happy to. No, I'm sure you will understand. I just want to say a little bit more before we get kicked out. So, okay.
Fine to like, no one is there, right? No one is there so far. So it's a good time. That's fine.
Okay, so the one big problem still that I want to point out is that theta is still present in the ciphertext. So information about the bit B is still present in the adversary ciphertext. Why? Or B tilde, I guess, is still present in the adversary ciphertext. Why? Because they could, if they had a bounded time, figure out theta, measure B in basis theta to get X, unmask B tilde using X, recover the bit that was being encrypted, and now store it, for example. And then there's no way you can delete if it's classically stored. So this is still a problem. In particular, we still need to remove theta from the view of the adversary to really make it so that all information about the bit is getting lost. So now we will transition to a final hybrid where the only difference from before is instead of encrypting theta, we encrypt garbage, zeros. And then the challenger defers sampling theta also until after the deletion certificate has been generated. So at this point, what we're sending to the adversary is halves of EPR pairs and an encryption of garbage 0 and like a random bit B prime. So that's what they're getting. And then B is determined afterwards by sample theta, measure in the theta, get your X, do the same thing as before. It's just done after the deletion certificate is generated. And again, we would now like to argue that 3 and 4 are close by the security of the encryption scheme. So because the adversary is polynomial time, cannot actually distinguish this encryption from the encryption of actual thetas. These two experiments should be close to each other. It turns out that that is quite non-trivial. Why is that? Because first of all, we want to reason about the experiment after everything is done, like the row and the bottom after everything is done, being close and independent of whether the bit B is 0 or 1. And on the other hand, once everything is done, we want to talk about statistical closeness here. And at the same time, we want to rely on computational security. So the way that we get around this issue is we define a predicate. Yes, we define an efficiently checkable predicate on the challenger's system after the adversary has generated the deletion certificate. So note that the system that the challenger has, we're going to try to define some efficiently computable function of this challenger system and say that that function cannot change depending on whether a theta was encrypted or zeros were encrypted, because otherwise it's efficient, and so you have an efficient attack against the encryption. So that's condition one. Now I'll try to see how much I can talk about what this condition is. And then the second thing we will try to argue is that if this condition on the challenger system holds, if the A registers of the EPR pairs satisfy this efficiently checkable condition, then the bit B must be completely uniform and independent of everything else that's going on in the system. And therefore, experiment 0 and experiment 1 are going to be close to each other. So we have to break down the analysis into two parts. First, fix an efficiently computable predicate on the state of the challenger after the certificate of deletion was generated, and show that whether it satisfies or not does not depend on what was being encrypted. And second, the fact that that holds is easy to prove in experiment 4, and therefore by the security of encryption should also be true in experiment 3. And by virtue of this predicate holding, we want to show that that means the bit B is independent of the entire system. So now I do have an explanation of what this predicate business is, but do we have some time? Do we have 5 minutes?
Don't come.
Okay.
Yeah.
All right. So, so this predicate is defined by taking inspiration from this previous work of Bowman and Fair, who talk about sample and estimate strategies for quantum cut and choose protocols. So consider the following simple experiment. There is a challenger that samples many EPR pairs, keeps half of them with herself, and sends the other half to the adversary. The adversary then claims to have measured all of these halves of EPR pairs in the Hadamard basis to get results x1 prime through xn prime. Okay? And sends the challenger, hey, here's what I got when I measured everything in the Hadamard basis. Now the challenger cannot, for some reason, check all these measurements. She can only check a few of them. In particular, she can sample a subset n of size n by 2 and check the adversary's claims on this subset only. And she wants to use these checks to infer something about the positions she did not check. So in particular, the challenger will check that for every I in this chosen subset, measuring her halves of the EPR pairs in the Hadamard basis returns an outcome that matches what the adversary claims it to. That means the adversary did indeed measure their own halves in the Hadamard basis. If this check passes, then we want to say that, then what the strategy says is we can conclude, just like in classical systems, if you send me a string and you claim that it's all zeros, and I want to check that it's all zeros, but I can't read all of it. So I'll check a few random positions and use that to infer that the rest must be zeros. This is analogous. It's an analogous quantum experiment, where now we've been given Hadamard basis measurements of a few of the qubits. And we want to conclude that for the positions that were not checked, those positions should also be close to Hadamard basis states. And that's what this paper allows us to prove. There's a formalization of what it means to be close to being Hadamard basis states, which I will not get into. So let me say very informally that what one can show is that each of these A registers, even on the positions that were not checked, as long as the check passes, these A registers on unchecked positions are close to the corresponding X values that the adversary claims them to be in the Hadamard basis. So if the adversary says that the first state is plus and the second is minus, third is plus, and so on, and you check a few of them, then you can trust that the remaining ones must be close to what the adversary claims. Now, why is this helpful? Because if these EPR pairs are all close to Hadamard basis states, and now the bit B is actually computed by measuring some of them in the computational basis, because recall that the bit was encoded in the computational basis. And now we have Hadamard basis states. So if you reverse compute the bit, it's going to be computed as a computational basis measurement on what is a Hadamard basis state. And this just gives you a random outcome. Like we said, if you take a Hadamard basis state, pass it through a computational basis filter, you get something random. So what's happening here is we're saying, well, if the adversary is able to, in this experiment 4, where we are sending the adversary halves of PPR pairs and no information about theta. If the adversary on a few positions is saying that they got Hadamard basis outcomes X prime, and we're checking those positions, then the remaining positions should also be Hadamard basis states. This again, note what is going on is adversary gets these.
So I guess most of the remaining positions would be Hadamard basis states, but a small number may not be, right?
That's right. Yes, most will be. Let's assume for now, just to simplify our life, that all the remaining positions are also Hadamard basis states. Then I just want to explain why that means immediately that the bit B is random and uncorrelated with the experiment. Why is that? Because we are measuring AI in basis theta I to obtain xi. But these AIs are all Hadamard basis states now, because the adversary has allegedly measured some of them in the Hadamard basis, and we check that they're Hadamard basis. So everything else must also be a Hadamard basis. So now all the AIs are close to Hadamard basis states. We'll measure them in the computational basis to obtain x's, and then we'll unmask our bit B with these x's. So these x values, which are computational basis measurements, will ideally be uniformly random and independent of the rest of the system. So that's the intuition. But now, like Vipul said, these are not necessarily all Hadamard basis states. Maybe the adversary measured a couple of them in the computational basis. What do we do about that? Turns out that, and this is a lemma that we proved in a previous work, we proved that as long as the system is sufficiently close to Hadamard basis states, it doesn't need to be exactly Hadamard basis. Computing the parity, the parity is still going to be uniformly random. So the exact lemma that we have is the following. If we have a state that is close to a sum of terms where each of these terms are Hadamard basis states, then the parity of measurements in the computational basis is going to be an independent uniform bit. So we proved that basically that XOR is a good, or parity is a good extractor for these types of quantum sources of entropy. This was in a previous work with my students Amit and Nishant, and also with James. The previous, but it was fairly recent. But yes, so we managed to prove that this is true, and so it turns out that being close to Hadamard basis in this sense of closeness suffices, and still have not been kicked out. So, do you want to go into like more details of what closeness is, or is that, yeah? Let me know.
This is sure. So is closeness just block theory?
No, closeness is, it's basically saying it's a superposition of terms that are low Hamming distance away from the claimed measurements of the adversary. So I can.
Yeah.
So note that the adversary claims that the state is supposed to be X prime in the Hadamard basis. What one can show it really is superposition of Y's, where Y are close in Hamming distance to X prime. So say that again. So here, what we ideally want is for the A registers to be X prime in the Hadamard basis. That's the ideal case. What we're actually able to prove is that A registers are nothing but a superposition over Y values, where each Y is close to the claimed X prime. Close meaning the Hamming distance between Y and X prime is smaller than C times N for constant C. And C can be made arbitrarily small, but for us it suffices to have C be less than half. So does that make sense?
So by the way, here at least it seems to me like even if you have a single qubit which is close to Hadamard state, then if you measure it in computational basis, the outcome is going to be uniform and the parity would be uniform. So isn't that enough?
Right. So what do you mean by a single qubit being close to Hadamard basis? You mean it's rotated like a small angle away from the Hadamard basis?
Yeah.
Right. So you can show that as long as the angle is like small, negligibly small, that this suffices. It's not what we get, or at least not immediately. So what we get is that some qubits can actually be computational basis states completely, like they're not at all Hadamard basis, but most are. And so we need to work with that.
Okay.
Yeah. And the closeness is also defined in this. The way at least we do it is we define it by being by talking about superpositions of Hadamard basis terms, which are low Hamming distance away from the claimed Hadamard measurement of the universe. Yeah, I can take any other questions.
Where can we find your paper online? Is it online?
It is online. Yes, yes.
On ePrint.
On ePrint and on archive, yes.
I guess you can thank Dakshita.
What about your slides? Can we find your slides online?
Maybe
I'll use this file somewhere.
Momentarily.
So those are notability images. If you use notability, then you can probably import them. I can send the slides over. I can send it to Kara if you want to share them.
Yeah, that would be nice. Thank you.
Thank you.